So I'm going to quickly talk to you about half-life and decay series. So a half-life is how long it takes for half of the atoms in a given mass to decay. And we count that in activity. And activity is actually measured in something called becquerels, named after the physicist Becquerel. So a Geiger counter is used to measure activity. 1 becquerel is 1 disintegration per second, and there's a video in this lesson about what a Geiger counter is and how it works. So the important formulas you need for half-life. We call half-life T with a little half as a subscript because it represents the half-time or half-life of time. And we say that the number of nuclei remaining after a particular number of half-lives can be found using this formula. And the number of half-lives in a period of time can be found using this formula. Essentially, this is how it works. If you have a period of time that radioactive nuclei have decayed, say it's 100 days, and say we know the half-life is 20 days, we would go 100 days divided by 20. Well, that's 5 half-lives that have happened in that time. So that's how we use this formula. Once we know what n is, how many half-lives, we pop that n up here. And what that does is it basically multiplies the original or starting amount that we had by a half that many times. So half to the power of 5 is a half times 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 a half, 5 times, multiplying what we originally started with, which basically cuts it in half that many times. So that's why we end up with half-lives. So what I'll do is go through an example with you. I wanted to just quickly show you something about half-lives as well. Some things have very long half-lives. So for example, things like thorium have a 14 billion year half-life. So half of the radioactive mass still remains after that many years. So imagine how long it takes to disappear. Things with long half-lives are often used for carbon dating, and you'll see there's a video on that in this lesson too. And things that have shorter half-lives are preferable if we're going to use them in the human body. We don't want these things to be hanging around. So things like technetium, and like sodium 24, they're used as medical traces. You can see here that some of the things that are a bit longer, like with the years, are used in cancer therapies. And here you've got americium, which is used in smoke detectors because there's actually a radioactive alpha decay source in smoke detectors that emits. And because alpha decay doesn't go through very much and it actually is stopped by smoke, that's how sad alpha particles are. If smoke gets between the alpha source and the detector, it basically knows that the alpha particles aren't getting through, there must be smoke, and the alarm goes off. So it's great that the half-life is so long because smoke detectors would effectively last forever if you had a battery that lasted forever. So that's why we have to change the batteries, but we never actually run out of the radioactive substance. So that's just knowing a little bit about half-lives. So I thought it would be also good to go through a question on half-lives here. So we've got, I'll just move that down a bit. So we've got a sample here of thorium, 234. It contains 8 by 10 to the 12 nuclei. And we've been told that it has a half-life of 24 days. How many thorium will remain after 120 days? Now the working for this is really easy. You can see it's here, but I'll just talk you through it. Basically, if we've lasted for 100, or we have a sample after 120 days, every 24 days the sample halves. So if we find out how many times the sample halves, it's 5 times that sample is halved, its value. So essentially you've had what you started with, which was, the 8.0 by 10 to the 12 nuclei, and you've done this. You halved it once, you halved it twice, you halved it 3 times, 4 times, 5 times to end up with a really small amount. Now the other way that we can write that with math notation is by calling it a half to the power of 5, and that corresponds to this little 5 here. So that's the working they've done there, and they've just put that in the calculator and found the answer. Now half-life graphs always have this kind of slopey thing going on, where initially the half-life is quite quick, or like the amount that's lost is quick because you lose half after the first half-life, but then you lose half of a half, which is a quarter after the second half-life, and then you lose a half of a half of a half, so half of a quarter, which is 12.5% after 3 half-lives. So you can see how every time you're actually losing less and less. So that's why we have this initial sharp drop and then like less and less that we're losing. So we'll do this example together. We've got radioisotope of sodium-24. Originally, I'm going to write down N0 because that's the original amount that it contains. We have 10 to the 10 nuclei that it contains. We've got a half-life, so T a half is 15 hours. That's the half-life. We know that the sample time, T is 150 hours. Now the first formula we have is N equals T over the half-life. So here all we're going to do is put T, which is 150, over 15, and we know that that's 10. So we have 10 half-lives that have passed in that time. So what that means is we've halved that substance 10 times. So to find the number of nuclei that remain, this is our formula. So we've found little n already. So we have n0, which is the amount that you started with. And then you have a half to the power of, in this case, it's the power of 10, because we had 10 half-lives that had passed. And if you put that into your calculator, you're going to find that it has a value, and that value is 9. So just put it in the calculator, by 10 to the 7 nuclei. So what you've done is you've used your two formulas, the half-life formula, that's just finding out basically how many half-lives have passed, and the formula here which tells you how many nuclei you would have at the end of that time. It can also be used for mass as well, so like if you knew a certain mass that you started with, then you could figure out the mass that you had at the end, knowing how many half-lives had passed over that time.